All right, so circuits. So here's a situation. Two batteries. Like batteries you put in flash lighters. And notice how they're hooked up. Positive terminal, one battery directly connected to the negative terminal of the other battery. Positive. So if we go from the top left of this thing, so let's get some colors going here. So if we start here, this positive end's connected to that negative end, so electric field, there's like a direction that makes sense. They're not opposed to one another. Through that battery, so current could conceivably go through the battery, so a positive end going through something connected to a negative end, et cetera, et cetera. So there's a nice pairing of things not opposing one another, like terminals would fight one another versus unlike. So here are some options, A, B, and C. There should be no current at all at B, meaning this, red area, this section of the thing, because all the electron current coming from the negative end of battery is used up in the bulb. So what would that mean? If it was used up in the bulb, then either it stops there or somehow it turns into light and leaves the bulb. Of course, it doesn't seem that it works this way in reality. The current just keeps moving and it has an effect in the light bulb. So we could probably dispense with that one. Or B, the current at B should be less than the current of A because some of the current is used up to make the bulb give off heat. So think about water running around in a closed system and turning, say, a water wheel. Do you lose water? No, unless you got a leak somewhere. You don't lose water. But that water wheel, there's a certain amount of energy that gets transferred to that wheel that you have to keep adding back to your water system. All right? Or should the current be the same at A as it is at B? Okay, so for part A, or can electrons ever be used up? Well, no. So the nature of that question kind of defeats itself. You can't use up electrons. They're either here or they're there, but they're not used up. Okay. So you can't do that. So the current's the same everywhere in the circuit. So at least in a series circuit, if there's one path for current flow, there's one current. In fact, we saw that once in one of our capacitor examples. There's one path for current flow, therefore the charge had to be same everywhere in the series capacitors. Okay, and so we've seen that once, that idea once in our electric potential stuff, right? But just keep that in your mind. If you have a single path for current flow, a series connection, there is one current value. It's the same everywhere. One current value. Now the voltage drop might be different across those things, but there's one current value. So we'll do some stuff on that later. So here, let's conserve energy. And there is this fellow. It's not Kirchhoff's or Kirchhoff's. Okay, too many H's and F's. Kirchhoff. That's the way you would say Kirchhoff. All right. Some books will call it Kirchhoff's laws. They're really just rules. But the reason why I call it laws is because they conserve energy. So let's think about this one. So here's just this path. These wires branch off, the fork in the road. And charges are conserved. What goes into a node has to come out of a node. So they split, and either they split up evenly or they split up unevenly, but you're not losing anything at that junction. Just more or less goes this way or that way. And so the node rule, and Kirchhoff came up with this to do circuit analysis, and we're going to do a fair amount of circuit analysis using Kirchhoff's rules. There's a node rule and a loop rule. They're both conservation of energy rules, but one of them is conserving energy in terms of current flow, and the other one's conserving energy in terms of voltage drops throughout the circuit. Right? So the idea here, gazentas equals gazatas. That's what I would, here's the gazenta, and here's the gozata. So current 1 would be what preceded that first little node. So really what you have here is I1, oops, get my colors consistent. I1 has to equal I2 because it's the same thing. I mean, it went into a node that had no split. So what you had on one side of that dot has to be what's on the other side of the dot. But then up here, I2 has to be the sum of I3 and I4. It can't be anything else. I2 just split up and went in two directions. So whatever the current flows at I3 and I4 are, they would add up to be what it was in the I2 region. Gazentas equals gozatas. You have one or more gozatas. Okay? We could have 20 gozatas, and that would be irritating to write that equation. But I can write an arithmetic equation that conserves the energy. All conservation laws are arithmetic. Sum of the parts equals the whole. So I3 and I4 are the parts of I2. I2 and I1 aren't parts of each other. The whole hasn't changed in that regard. So the two ways to... this picture shows us two versions of the node rule where you have one gazata versus two gazata, and you could keep layering that many gazatas as are needed. All right, so here's an example. What is I3? So this part up here, what is I3 if I1, which has to equal, I1 will equal I2, okay? Right? And I4, the other part here. So it has to be that if we just write the same equation I wrote before, I2 or I1 equals I3 plus I4, we just solve it for I3, because I know 2 out of 3 things. So right here, I1 equals I2, and I2 has to equal I3 plus I4. I already wrote that on the previous screen. So I1 here is that 3 times 10 to the 19th electrons per second. I4 is this 7 times 10 to the 19th electrons per second. And it's just an algebra, simple elementary algebra equation. Solve it for I3. So the difference, negative 4 times 10 to the minus 19 electrons per second. Now typically we'll be talking about amps, whole amps, milliamps, those sorts of things. We'll use a particular unit for current flow. But this is preceding us developing that unit of measure, just applying this rule. If I have this many per second, et cetera, okay? So kind of a simple rule, but it conserves energy, and that's really that we conserve energy. One of the things, and this will become clearer as we actually get into circuit analysis, is the nice thing about Kirchhoff's rules is you can make an assumption about the direction of current flow, which is what we did in the picture. But when you go to put the data in, if you get a negative out, that means that assumption was wrong. Because you can have positive and negative current flow. Right? And so when we do circuit analysis, the nice thing is we can go, you know what? If it's flowing these ways and those ways, all right? We write our equation, it stops being physics, and it becomes a math problem. And at the end of that, if my current ends up being a negative, then I flip my assumption. Because it'll be the right magnitude, it'll be the wrong direction. That's the nice thing about it is it's immune to my assumptions if I do the math correctly. And the only thing that'll be wrong is my assumption about direction. The magnitude will be right, the sign will be wrong. That's it. And so we'll get to that. Not today, that'll be later. But just kind of a warning there. All right. So we'll stop, drop, roll away from Kirchhoff's rules for a minute and think about the way this is playing out. So we're going to keep digging deeper conceptually into what's going on in here. In fact, we're going to do that a lot because there's a lot of very non-intuitive things about why current flows the way it does. And so we have to explore that. That takes some time and detail. So let's just think about the situation here. So there's a statement. A mobile electron cannot push any other mobile electron through the wire because the net force of the mobile electrons and positive cores is 0. So there's this equal and opposite reactions. It's essentially Newton's third law game here. And so one of the mistakes conceptually that people make is think, oh, well, the electrons at this stage are pushing the ones that are ahead of them. And that's false because they're all in balance with respect to one another and the cores. So something else is getting them moving, and it's the electric field. And the way to think about that would be literally like you saw in those videos, or if, like up here on the desk, of course you can't see it in the video if you're watching this lecture, but this ruler is laying flat on the table. And so let's say it has mobile, like let's say there were some balls or something on it, and they're not going to move, but if I lift one end, which would be equivalent to applying a voltage to the wire, an electric field, now they're all going to start moving. And that's what, something else is causing them moving. They're not pushing one another, something's pushing them. And it's pushing all of them in the same way at the same time. They're not pushing one another around. They're running into one another, but their fields are not pushing one another around because they're balanced out with the cores, on average. Not obvious, but is a conceptual error. All right, here we go. Finally, we reveal your typical drift speed, 10 to the minus 5 meters per second. We're talking fractions of millimeters. Thinking, dang, because what's weird is that these electrons are moving at thousands to millions of meters per second. Individually, they're going blazingly fast, but they're zigzagging all over the place. So as a collective, they're moving insanely slow. All right? In that regard. Now, here is a factoid. The mobility in copper is this other number. So what's the magnitude of the electric field in a wire that has a copper wire, which has a particular electron mobility based on its material structure? And if we give this typical drift speed, what does that give us? Well, apply the equation. Drift speed is the electron mobility times the field, so solve it for the field. And we have this really small electric field. 11 1,000ths of a Newton per Coulomb. So remember in Newton, to think about it in force terms like weight, something we can relate to, a Newton is a quarter pound. So let's go to McDonald's, get a quarter pounder, all right? So a quarter pounder burger, we'll assume it weighs a quarter of a pound, all right? Well, the patty does, the burger weighs more, obviously. So just a burger patty, big burger patty, quarter pound burger patty. How much does that weigh? Doesn't weigh a lot. And so that's how much force we're talking about. Let me rephrase that. We're talking about 11 1,000ths of that burger patty. So if you could chop that burger patty into 1,000 pieces, pick out 11 of them, that's the weight force, if you wanted to think of this metaphorically as a weight force, that's being imposed on each coulomb of charge. Okay? That's really small. 11 1,000ths of a quarter pound per coulomb. That'd be our. You always try to put it in terms that we can relate to, because we don't do metric measures, newtons and whatnot, coulombs. We just don't think in those terms. This is America. We deal with pounds and inches and stuff. All right. So we got to make some analogies to try and imagine that. But you think about it, thousandth of a Newton on something as small as electrons, that's a lot. But it gets it moving. It doesn't take much to have current flow. And we have current flow because we have a non-zero drift speed. So a drift speed, the lights that are on in this room, the drift speed of the electrons going through the wires that lead to these lights is on par with what's in this problem. We're talking millimeters per second at best. And pretty much everything that runs on electricity, the drift speed of the electrons, of the mobile electron C, is this insanely slow thing, but yet it lights up all the lights, it runs the computers, et cetera, et cetera. And that's because you have these gazillions, literally 10 to the 18 or more electrons per second moving a millimeter. So let's think about it, though. Let's just say that these electrons are moving 1 millimeter per second as a group. Well, for something as small as an electron to move an entire millimeter, that's fast. Okay? That'd be like us moving a mile in a second. In fact, if I were the nucleus of an atom and you were my electrons, at our scale size, you need to get about 2 miles away from me to be in your spot in orbit. Okay? So, they're moving, relative to their size world, they're moving and grooving. And macroscopic, they're barely moving in that regard. So, things you can't get from a book usually. All right. What happens if the wire changes thickness? So what we're sitting up here for is resistors. So when we start with circuits, we talk about batteries and resistors. Then we start throwing in light bulbs. We've already dealt with capacitors, so we'll put those in the mix as well. But the next thing to deal with is a resistor. And incandescent bulbs are basically special material resistors, sort of like if you think of the old stoves, they have that curly Q burner, and that's just a big resistor. Jam current in it, it gets hot and glows. All right, so light bulbs are similar to that. So we have this old news here. Current is this mobile density. That's what the N number was of the electron C. Area is the cross-sectional area, and then the drift speed. Well, the area that you have here cross-sectionally is different than the area you have there. We have a flow restriction. we go from a lot of flow area to less flow area. Okay, so something's got to give in that game. Current flow must always remain the same throughout a circuit. And the caveat here is we're still talking about a single path. We're not talking about splitting off into multiple paths. Because if you have multiple paths, you can have multiple flow rates. Not necessarily, but it's possible. So we're still talking about a single path, namely the one we're looking at. Okay? So something else changes since the flow rate has to be constant throughout the pipe. And so what's that going to be? So what do we have here? Area thin, drift velocity in the thin. Area thick, drift velocity in the thick. Okay? Mobile electron density, that's not going to change. Same material. So what can we do? We can solve it for thin. And what do we get? The ratio of those areas, okay, is going to be the thing that basically forces the drift speed to be different in that area. So, wait a minute, you just told me that the flow rate doesn't change. Correct. The drift speed changes, but what is happening is I'm cramming more of those things into a smaller space, but it's still the same number of things per second going past any particular line in the sand. So in the thick part, they're all going a slower drift speed, okay, through there, and then when they suddenly get crammed, everything has to pick up speed so that things can keep going through this same number of things per second going past any particular line in the sand, if you will. Okay? So, we do these ratios and get that sort of thing going. Now, what we can do, all right, is remember that this is what V is. All right, so I'm going to kill that color connection for the moment. That is drift speed. Electron mobility times electric field is drift speed. Just remember, so we'll come up here and we'll say in a, well, it's not mu, it's just U, U, E. All right, so just going back to the equation we developed a lecture or so ago. And so we can substitute that, and that ratio gets to stay out in front like it was before, okay? And so now we're changing our viewpoint from a speed conversion ratio in terms of area to now an electric field ratio to area ratio. Okay? So we're able to get how the electric fields in these regions are going to be related. So we could get anything we wanted out of this. What's the electric field going to be if I change the geometric property of the wire in some way? So typically you don't have a wire itself that changes its thickness, but you'll have a device There'll be a resistor. The thin part of this wire is going to be a resistor. It's going to resist flow. And so things change in that resistor. So as I was describing earlier, the mobile electrons have to speed up through the smaller area. That's the only way you can maintain a constant number of electrons per second flow rate, is if they speed up in the compressed area, slow down in the larger areas. And it's literally just any place I draw a line and count how many are going past that line, it's going to be the same everywhere through the circuit, even though the drift speed's slower here than it is there. Okay. Hard to see, not exactly intuitive, unless you have experience with systems that flow. Not everybody gets to play with water and whatnot. All right. So here's the thing. This statement here. Admittedly, this is not obvious, but I want to dwell on it for a moment. Different devices within a circuit, okay, and we're just pretending we're doing different thicknesses of wire, standing in place for something more complicated, will have different voltages, and the reason for that is the distance over which those things act will change the voltage. So if I just multiply D to each one of those E's, I have a voltage. So this works out to be voltage. So we'll lay this out in a minute. Different devices will have different voltages, which is directly related to the electric field and the distance over which the electric field is applied. Okay? And they maintain they do these changing things to maintain speed. All right. Conventional current equation, we've already worked that out. I'm not going to dwell on that. This right here, those are those material properties. So is A. All I want to, this is just kind of an emphasis, and just particular emphases about these formulas. Separating what are material properties from measured, things you measure or control. So N, U, and A are material properties. I can measure A, N and U are constants. E is something I control, and charge is going to be something fundamental to it as well. Here, current density. If you remember, we talked about area densities, like surface area density, how much charge is on a surface. We talked about linear density, if things are lined up along a length dimension. We have volume densities, that's what you're most familiar with before a course like this. Say in chemistry, density was always mass per unit volume, etc. Density was always a volume thing. Then we upset that apple cart and deal with linear densities, area densities, as well as volume densities. So now we're going to have a current density, but the thing that makes sense for current density is with respect to that cross-sectional area. So not pictured here, but what we did elsewhere, here's a wire, okay, and there would be this this area right here, this cross-sectional area. There's some sort of current, electrons, which are blue, always, just kidding. There has to be a density of current going through that area. And so current density, this new thing, is just how much our conventional current flow, which we've labored long to get a big I equals some stuff, how much of that per unit cross-sectional area? Current density. It's an area density thing. We'll have a few problems on it. The vast majority of our work is going to be circuit analysis. We'll have some homework that is just these theoretical things like you've seen exampled here. We have a whole separate lecture on circuit analysis, multiple homework sessions on that. Okay, but here we're just kind of setting up all the theoretical stuff. So guess what we do again? We create yet another compactification. Just made up a word, I think. This Q in U business up here, we call it conductivity. So let's think about why we would call that conductivity and give it a new symbol. Well, each material N and U are going to be particular constant values for any particular material. So copper will have its own NU. Aluminum will have a different NU. Iron will have a different NU product pair. And the charge, that'll be however much charge is free to do that. So conductivity, these three things, every metal will have its own conductivity. So it's more efficient to collect the things that deal with what are the fundamental properties of the material that make it a better or worse conductor than some other material. Why is gold the best conductor? Why is, gold is our best conductor, but we don't put gold wires in our houses because it's expensive. Copper's an affordable option. That's also really, really good. Aluminum, they used that for a while, and I forget why we went away from aluminum. But you can have aluminum wires, and I'm spacing. I'll think of it later, probably, or we Google it later. But they went away from it. It was not reliable. I don't know that it was unsafe, but it wasn't as reliable as copper. And so, anyways, so we do this. So our conductivities. Now you could look up conductivities for the metals, just like you could look up the densities and electron mobilities of them. All right. And then that lets us do this nifty little thing where our current density, J, now can obtain a direction because it's related to the electric field. This ultimately is why current flow is the opposite of electron flow. Notice that the current density, so just little vector memory thing. So whatever J is and whatever E is, they're pointing in the same direction. Okay? Electric field, we were on that day 1 or 2 of the course. We started with Coulomb. So electric field points from positive to negative, period. All the time. And if a positive charge is in that field, it will get repelled. It'll get pushed from the plus to the minus. But the positive charges aren't moving. The positive charges are fixed. It's the electrons, minus charge things, that are getting pushed from the negative to the positive. But what we just worked out is that current density is moving in the direction of the electric field. But the things that carry charge and move in the circuit are going the other way. Okay? So we have electron flow, which is the reality, and we have current flow, which is a mathematical reality. And mathematical reality is often nothing like actual reality, physical reality. And again, it goes back to nobody had the nerve to just say, look, we goofed it, let's turn everything around, change all the textbooks. We didn't do that. So we're stuck having to constantly account for the fact that, are we talking about electron flow or current flow? Current is related to electron flow through all of these equations that we've passed up. Right? And so when we do our simulations, all of our simulations are electrons moving. So one of the things we'll do with circuit analysis, we'll have a problem, we'll work it out, or go build it in the simulator, and notice that everything's going the other direction. That's because the simulator is electron flow. Our equations are conventional flow, current flow. So just knowing that is important. And I kind of already just said this. And I'll post the full notes like you're looking at now on screen in case some of this gets missed. So this right here, I am still so bothered that historically we never did this. We imagine positive charges moving in the direction of electric field. That's what we have to imagine that because that's what the math tells us to do. But it's false. Electrons are what's actually moving, and they're going the other way. Just to emphasize that again. All right. Now, we're going to talk about resistance. I have a T-shirt that's worn out, too worn out to wear to work. Resistance is futile, if less than 1 ohm. So the Star Trek thing with the board, okay? And ohms are a measure of resistance. And now we're going to build the idea of resistance, which is related to conductivity. All right? So here we have this memory that I'm sure you absolutely recall the fact that a change in voltage is the electric field times the distance over which that field is applied. We wrote it ED, ER, or EL for the length. Now, because we're going to talk about the length of the resistor, which could be like the length of the thin tube part that we just worked out. You know, how the drift speed changes. So, and we just worked out this, okay, that current density, and in fact we were talking about this in vector form, okay, if we wanted to. They were vectors a second ago. This is current density right here. Conductivity, which was a compilation of the mobile density, the electron mobility, and the area for flow. And current density was how much current per unit area. It was an area density issue. So just kind of review of what we just developed. Not going to pretend that everything made perfect sense or was even remembered. All right, so we got to do that. So we can take these two things, the new thing that we developed today, the old thing that we developed weeks ago, and we put them together because they're related by the electric field. So literally what we have here is basically solving for the electric field. Okay, so the electric field would be delta V per L, and if I wanted to have conductivity, so then we get this new equation. So current density ends up being related to these other things. So let's think about this for a minute. The current density, how many electrons per second per unit area, okay, is dependent on this new thing called conductivity, which is a compilation of material properties. So I think that's easy. Copper has a different conductivity than aluminum, et cetera, et cetera. And it's all material properties. We've been dogpiling the number of material properties into this one new thing called conductivity. That's a global measure considering all of the features of a material. All right? Then what we're saying is that that current density is directly related to the conductivity of the material. It's also directly related to how much voltage. More voltage, more current. If I pump up the pressure more, I get more flow. If I raise the ramp, I go faster at the bottom of the ramp. So that, think of voltage in a gravitational metaphor, all right? But it's inversely related to the length. So the longer that I have to push, so the longer the resistor, or the longer the path, that brings things down. That takes a chunk out of how much voltage. So the longer the thing, the bigger the voltage needs to be. Okay? So these make sense, but they're absolutely necessarily true given the equations we've already developed. But this is just trying to make some sense out of why would the current density be directly proportional to this and that, inversely to the other, okay? So solving this for current, try to get it back into something that we're doing. We have this, and so this right here, you know, what am I going to call this L over conductivity area? It's a new thing, all right? And it happens to be I can write it this way. So this, taking this right here, all right? Let's just pull that out for a minute. Rearrange it. And we have basically a length per unit area. So now I've isolated geometric properties of this device that's in a circuit, which will be unnamed. It's a resistor, but we don't know what it is. Just this, there's a length and a cross-sectional area for this region of a circuit, sort of like the thick and the thin part. And purely geometric pieces of the puzzle, and then this material property involved in the puzzle. So what's the inverse of conductivity? Well, bigger conductivity means it conducts electricity better. Smaller conductivities would mean that it resists. So the inverse of this thing is what we call resistivity. So conductivity, and if you flip it over, you have a thing called resistivity. Okay? Which one's better? Well, it all depends on what you're paying attention to. All right? What's the particular viewpoint? So we call it resistivity, and we give it a rho, so we're using a symbol that has the same letter value, so to speak. So now, this thing becomes that thing just by moving conductivity to the numerator turns it into resistivity. So now, I have a length per unit area. So let's think about this. Let's think about a tube. All right? Resistance increases as the length of the conductor increases. And the reason for that is as you add more chunks of length, there are more things to run into. Okay? So if you're trying to go from one end of this building to the other, and there's 100 people in the hallway, there's a lot more resistance to your motion than if you're just trying to go from one end of the hallway to the first door that you see. You will encounter less resistance the shorter your path. Does that make sense? So resistance is directly proportional to the length of the circuit path. More circuit path, more resistance, because there's literally more to run into. However, it would be inversely related to the cross-sectional area. If I increase the cross-sectional area, I'll lower the resistance. So somehow this hallway could magically become wider, or you could fly over people, all right? Then your resistance to motion goes down because the area increased. But if for some strange reason the hall got smaller, like there was barricades by the wall, then guess what we got to do? We got to cram more stuff into a smaller space, which means it's easier to run into stuff. There's less loopholes, if you will, to get past that. So this allows us to talk about resistance. 2 out of 3 factors in resistance are the geometry of the material. And then the other factor is essentially the conductivity of the material, pitched in terms of resistivity instead of conductivity. Right? So lots of mathematical layers in here. And we call this thing we call it resistance. All right? And what that means is we get Ohm's law, which is voltage equals current times resistance, or we can write it as current is voltage over resistance, etc. We'll use the heck out of Ohm's law in our circuit analysis, which is why we went through all of this trial and tribulation, because we have this amazingly simple formula, but where did it come from? Okay, it came from all that analysis, okay, which is a lot. Okay, so it's a really simple formula. We'll verify it, we'll use it, and it will take us, and it applies to anything in a circuit: capacitors, resistors, light bulbs, any load that's in the circuit. Okay, so that's